As we start our look at organic chemistry, this is a Reuters photo from the 2010 BP oil spill in the Gulf of Mexico. On April 20th, an explosion that killed 11 people started the nearly 5 million barrels of crude oil, petroleum, that was released into the Gulf of Mexico over the course of about 3 months. That's the largest oil spill in the petroleum industry's history. What is petroleum? Why is it so valuable? And what's up with these gas prices? Throughout this chapter, I hope we can explore some of these questions as we focus on organic chemistry, the chemistry of carbon. The first section of this chapter is only about hydrocarbons, a review term from last semester. So I bet you already know that hydrocarbons are covalently bonded compounds containing only hydrogen and carbon atoms. In this section, we'll see how from just these two atoms, an entire branch of chemistry is formed, with millions of compounds. Don't worry, we'll look at only a few of these. We were not going to look at the millions, but the foundation in this chapter will give you what you need to be able to understand organic chemistry in a way that can be expanded to those millions of compounds. Organic chemistry is the study of carbon and compounds containing carbon. Remember that carbon monoxide, carbon dioxide, CO, and CO2, and any ionic compound that has carbonate in it, those are not included in the study of organic compounds. Why is carbon so special? Let's look at its location on the periodic table. Carbon has an atomic number of 6, so an atom of carbon has 6 electrons. It is in group 14, so we know that it only has 4 valence electrons. How many other nonmetals have 4 valence electrons? Oh wait, that's a trick question. There are no other nonmetals that have 4 valence electrons. Carbon is special. It can bond up to 4 times, so it can make long carbon backbone chains and carbon rings, and even bond easily with oxygen, nitrogen, and hydrogen to make the complex molecules of clownfish and you. In this section, we'll look at saturated hydrocarbons and unsaturated hydrocarbons. But let's focus on the saturated hydrocarbons for now. A saturated hydrocarbon has only single bonds, no double or triple bonds. So as a result, each carbon atom is bonded to exactly 4 other atoms. I like to think of saturated hydrocarbons as containing the maximum number of hydrogen atoms for a certain number of carbon atoms. It's saturated by hydrogen. Saturated hydrocarbons are also known as alkanes. Notice the A-N-E, ane, ending of the word alkane. That'll show up again in a moment. Alkanes have the general formula CnH2n plus 2, which means that an alkane always has 2 more hydrogen atoms than twice the number of carbon atoms that it has. For instance, an alkane with 1 carbon atom will have 2 times 1 plus 2 hydrogens. In other words, 4 hydrogen atoms, CH4. An alkane with 2 carbon atoms has 2 times 2 plus 2 hydrogens. So its formula is C2H6. Again, because carbon can make 4 different bonds with its 4 valence electrons, organic molecules are extremely versatile. Let's start by looking at the simplest hydrocarbons, alkanes with no branches. These are known as straight-chain alkanes, and you already learned how to name these last semester. A 1-carbon straight-chain alkane is called methane. 2 carbons, ethane. 3 carbons is propane, and 4 carbons is butane. Notice how all 4 of these have that ane ending, just like the word alkane does. The naming of simple straight-chain alkanes forms the basis for naming all organic molecules. Also notice how each time carbon is added to make the chain longer, 2 hydrogens are added as well. These long-form molecular models are called structural formulas, and they are easier and quicker to draw than electron dot formulas, but there's got to be an easier way to represent an organic molecule. Condensed structural formulas can be used to show organic compound structures by condensing the carbon-hydrogen bonds into CH3 or CH2 units, as shown here. See, ethane becomes CH3CH3, propane becomes CH3CH2CH3, butane becomes CH3CH2CH2CH3, where each CH unit is a carbon atom with that number of hydrogens bonded to it. Here's a comparison showing some other models of alkanes. The ball and stick model, that helps show the three-dimensional nature of the bonds, something we'll model in lab later, and the space-filling model. The space-filling model helps show the three-dimensional nature of the molecule with a more realistic view of the electron cloud overlapping when it forms covalent bonds. Here are the first 10 alkane molecular formulas, names, and condensed structural formulas. You already learned the organic prefixes, meth, eth, prop, and bute, and the Greek prefixes, pent, hex, hept, oct, non, and dec. You learned those when you learned to count to 10 with the prefixes last semester. Perhaps you even learned a handy mnemonic like Mary eats peanut butter pancakes, happily hopping over 9 dinosaurs. Take a look at the formula for octane. Octane has 8 carbons. Because it's a straight chain alkane, it has, you guessed it, 18 hydrogens. That's because 2 times 8 is 16, plus 2 is 18. Here are 2 alkanes, both of which have 4 carbons and 2 hydrogens. The one on the left is butane, and the one on the right is called 2-methylpropane. Do you notice any differences between them? Perhaps you notice that butane's carbons, represented by the dark gray spheres, are all connected in one continuous chain. And that 2-methylpropane's carbons are connected such that one of the carbons, this one here, is branching off of a 3-carbon chain. These 2 structures together are called isomers, something we'll learn more about later. But for now, let's be sure we just understand the difference between a straight chain alkane on the left and branched alkane on the right. Gasoline is a petroleum product. There's no formula for gasoline, and there's no such thing as a gasoline molecule because gasoline is a mixture. It's a mixture of organic compounds. Chief among them is octane. Perhaps you've heard of octane rating. The octane rating of gasoline measures how uniformly the hydrocarbons in the mixture burn. Ringed hydrocarbons and branched hydrocarbons burn more uniformly than straight-chain alkanes. So a higher octane rating means that there's a higher percentage of the ringed and branched hydrocarbons than the straight-chain hydrocarbons. If your engine is knocking, you might want to try a higher octane gasoline. Of course, my rule for purchasing gasoline is to purchase the cheapest octane rating that the owner's manual for your car suggests, provided that the engine doesn't make that annoying knocking sound. Since we're on the subject, let's go ahead and define them. A cycloalkane is a hydrocarbon with only single bonds, just like an alkane, but in which the carbon chain is connected back on itself to make a ring. When naming these alkanes, just add the prefix cyclo to the name of the alkane. For example, a 5-carbon ring is called cyclopentane, and a 6-carbon ring is called cyclohexane, shown here at the left and the right. Notice that each carbon atom in the condensed structural formula is still bonded to exactly 4 other atoms. With cycloalkanes, we can further condense these structures and only draw the geometric shape that the carbons make. Each corner in the pentagon of cyclopentane represents a carbon atom bonded to the appropriate number of hydrogen atoms. In this case, 2 hydrogens each. And likewise, the 6 carbon atoms in cyclohexane form the hexagon. Give you a moment here to write these down in your notes. Petroleum, natural gas, and coal are known as fossil fuels. These organic molecules with which we use as fuel were once used by prehistoric plants and animals to form useful things like plant cells and dinosaur teeth. When these prehistoric plants and animals died, though, millions of years of heat and pressure caused their organic molecules to form things like petroleum, coal, and natural gas, hence the name fossil fuels. Natural gas is primarily composed of methane, CH4, which is what burns when you use a gas stove or a water heater. You've seen methane combust every time you used a Bunsen burner in lab, too. Natural gas is not just used for burning, though, since it's the raw material for many of the organic compounds we'll talk about in Section 3 of this chapter. Petroleum is a mixture of alkanes and cycloalkanes. Crude oil is used to make gasoline, jet fuel, kerosene, diesel fuel, fuel oil, asphalt, lubricating oils. Yeah, it's pretty useful stuff. With such a complex mixture, how do you think we're able to separate it into its individual components? If you were thinking some sort of distillation process, you were thinking correctly. Because different components of petroleum have different boiling points, distillation can be used to separate the mixture. Oil refineries, like the ones pictured on the previous slides, use a process called fractional distillation, in which the distillation process is repeated over and over again to produce several separate mixtures. These mixtures are called fractions. Here we see a diagram from your book that outlines the process of fractional distillation. Basically, the entire mixture is heated up to about 700 degrees Fahrenheit. At this temperature, most of the mixture's components will be in the gaseous state. Those that aren't are called residue and can be drawn off the bottom. As the gases move up the tower, the temperature slowly decreases, and some materials condense. Those with the highest boiling points condense first. And some materials that aren't condensed will continue to flow up the tower. Once those condense, as liquids, they can be drawn off from the mixture of the gases, as the gases keep going up. At the top of the tower, only the lowest boiling point substances will stay in the gaseous state. These volatile gases, like methane, ethane, and propane, can be collected from the top of the tower. Remember that boiling point increases with molar mass. So as a result, the heavier, higher boiling point compounds condense near the bottom of the tower, and the lighter, lower boiling point compounds condense towards the top. Why do you think methane, ethane, and propane have low boiling points compared to the longer hydrocarbon chains? I hope you were thinking about interparticle forces because that's the right track. Small molecules have weaker interparticle forces, so they don't need to be heated up as much to overcome those attractions and cause those molecules that are sloshing around as a liquid to become the gaseous molecules flying all over the place. At high temperatures or through the use of catalysts, large hydrocarbon chains can be broken down into smaller hydrocarbons using a process called cracking. This is how we can take long molecules and get more useful shorter molecules out of them. Did you know that gasoline used to be the leftover molecule from the cracking process used to make kerosene back when no one drove cars and everyone had kerosene lanterns? Those large hydrocarbons can also be converted into other useful organic compounds through a process called reforming. We'll talk more about those other organic compounds in Section 3, though. Let's finish up our look at fossil fuels and consider coal. Coal is pretty much just pure carbon. Coal is used mostly as fuel for combustion, like the combustion you use in your charcoal grill to cook up some hot dogs on the 4th of July. This is the end of the introduction to hydrocarbons. Don't worry, the other lectures shouldn't be this long, but we just learned a lot about organic chemistry. Next time, we'll look at how to name alkanes with branches, like the 2-methylpropane molecule you saw earlier.